Hello everybody. So let us now continue further our discussion with respect to gas hydrates, and we would also look at some of the interesting aspects of solid state inclusion complexes in the present lecture. So to start with, as we discussed in the last lecture, that gas hydrates essentially have water as a supramolecular host structure, and then which is extensively hydrogen bonded, and then the voids contain the different kind of molecules which act as gas. So in this case, the basic framework comes from hydrogen bonded water molecules, and efforts have been made to determine the crystal structures of these gas hydrates. So to start with, the structure is determined from X-ray diffraction for these particular gas hydrates. And what has been observed, there are two fundamental building blocks which are present in the formation of these gas hydrates. So we have got this 1, 2, 3, 4, 5 membered ring. So you can essentially approximate it to be, this is a linear OHO hydrogen bond. So this is a 5 membered ring. In addition to this, it has also been observed that you can have so 1, 2, 3, 4, 5, 6 membered rings as well. So these kind of building blocks are present, and also it is essentially the fusion of these 5 membered rings and the 6 membered rings which gives rise to these kind of gas hydrates. And what has been observed is the following. Now if you look at the diagram here, that we can have different kind of 3-dimensional supramolecular building blocks of these water molecules. For example, the top row here represents, the first figure represents a pentagonal dodecahedron, because it is represented symbolically as 512, essentially telling you that there are 12 such 5 membered rings which are fused to form the dodecahedron, and each vertex actually represents the water molecule, and the bond essentially is not a covalent bond. The line which connects the two vertices essentially corresponds to the hydrogen bond. So this is not a covalent association, it is a geometrical diagrammatic representation of a hydrogen bonded assembly, where we now know here that each pentagon here is this 5 membered ring and each hexagon is the 6 membered ring. Each vertex is a water molecule and the lines essentially represent the hydrogen bonds. So this structure is referred to as a pentagonal dodecahedron. We can also have another kind of structure which consists of fusion of 12 5 membered rings and 2 6 membered rings. So you can see the 6 membered ring, this is one 6 membered ring and this is another 6 membered ring, and the remaining 12 5 membered rings are also present. You can see that as well, 1, 2, 3, 4, 5 and 6 here, which is this side. and similarly you can see 1, 2, 3, 4, 5, 6. So there are total 6 plus 6, 12 5-membered rings as well as 2 6-membered rings, and this creates the structure which is called a tetrachedecahedron. The tetrachedecahedron, that means there are 14 such rings. The total number of rings is now 14, 12 5-membered rings and 2 6-membered rings. Similarly, we can, along the same lines, we can get larger sized clusters, larger sized supramolecular hydrogen bonded building blocks consisting of this 5-membered fusion of these 5-membered and 6-membered rings. We can also have 12 such 5-membered rings which undergo fusion with 4 such 6-membered rings. You can see the 6-membered rings. This is one such ring in the front, there is one at the back, there is one on the right hand side and there is one on the left hand side. So there are 4 such 6-membered rings and the remaining 12 5-membered rings are also present. This leads to the formation of a hexachedecahedron. That means the total number of fused rings is now 16, and the bottom row represents an irregular dodecahedron, that is this one, and we have the famous icosahedron or the icosahedral structure also, which can be present in different gas hydrates, in the structure of different gas hydrates. So keeping in mind these the composition of these building blocks, that we can either have the fusion of 512 unit with 512-6-2 unit, or the fusion of 512-6-4 with 512 units. We can have different types of structures. So 2 structure types have been reported. The type 1 structure type is a fusion of 2 512 units and 6 512-6-2 cavities. So each of these supramolecular building block creates a cavity. You know, there is a cavity which is present in the center, and this cavity can now include the guest molecules. It can now include the guest molecules, and the number of the guest molecules can vary depending upon the voids or the volume which is available for the different guest molecules to occupy the voids created by the host cavity. The second one is a type 2 structure, which is a fusion of 16 512 units, 16 such number, and 8 512-6-4 cavities. So now you have a fusion of 16 such 512 units and 8 such 512-6-4 units, and these are the 2 fundamental structure types which have been observed. And as I told you, the 512 unit is the dodecahedron, and the 512-6-4 unit is the hexachedecahedron, and the 512-6-2 unit is the tetrachedecahedron. So now these are the 2 structure types which are present, and let us look at how these structure types look like before we go further into their geometrical properties. So this is the structure, you can see, of the gas hydrate of the structure 1 type or the type 1, we can call it 1 S1, okay, or type 1. So you can see here that you have got this central dodecahedron, that is the 512 unit. This is the 512 unit, which is surrounded by the tetrachedecahedra, which is surrounded by the tetrachedecahedra. 1, 2, 3, 4, 5, 6. There are 6, and there are 2 more actually which are behind. So here I am showing you a representation of 8 tetrachedecahedra. You can even have 2 more in front of this dodecahedra, but by definition, as I told you, that to start with, type 1 is a fusion of 2 512 units and 6 512-6-2 5, 12, 6, 2 units. So we have the 6, 1, 2, 3, 4, 5, 6 structures, as well as 2 are shown behind for the sake of completion. So this is the structure of the S1 type. In the S2 type, you can see that we have got the fusion of these 512 units along with the 512 6/4 units. That is, we have got the hexachi-decahedra which are actually fused. Now you can see the hexachi-decahedra, they are present here 1, 2, 3, 4, 5, 6, and this gives rise to a void in the center, which is actually a dodecahedra void. This is a dodecahedra void, and it is these voids which are now present, whether the dodecahedra void or the hexachi-decahedra void, which are available to the guest molecules for being occupied. Okay. So this is the structure 2, the structure 2 gas hydrate, which actually is a fusion of the hexachi-decahedra, 6 such units, forming a dodecahedra in the center, which creates the voids, and in all these voids we can have the guest molecules. Now there is a third very important structure type. We call this the structure H type, which is actually also the hexagonal form of ice, which we use for the sake of comparison here. And in this we will see that we have got a central icosahedron which is surrounded by 1, 2, 3, 4, 5, 6 irregular dodecahedra, and the central part is the icosahedron. So this icosahedron is formed by the fusion of this irregular dodecahedra, and the composition of this particular structure type depending upon the presence of different guests, which are represented as 1x, 3y and 2z, along with 34 molecules of water. This is the composition of the unit cell. This is the ideal composition. This is the ideal composition of the unit cell if you were to have the filling up of the X type, Y type and Z type voids along with 34 molecules of water. But let us also go back and just look at the composition of the type 1 and the type 2 structures. So S1 and S2, these are more important and fundamental. So the lattice type, because we have determined the structure of these gas hydrates and therefore it corresponds to a lattice, and the lattice type along with the space group, which corresponds to the symmetry operations which define the position of the molecules in the unit cell. It is the body centered cubic PM3N, and for the and S2 is the diamond cubic structure, which is the face centered cubic. FD3M is the point group, is the space group. The unit cell length in angstrom is 12, this is 17.3. Now what is the unit cell formula? This is very important because we will be taking this unit cell formula further to understand the composition of the host and the guest ratio. So unit cell formula here is 6x 2y 46 water, whereas for the large sized S2, large size cavity, 8x 16y 136 water. So right away you can see that the composition of the unit cell is very different. S2 being a much larger size cluster, see this is S2, it is a much larger sized structure, and the voids are also available more in terms of volume. So we can have larger number of guests which are being included. And what is the nature of the cavity? This is important. So, it can include small y and large x. This can also have small y and large x. So, if you have got two different kind of host molecules, depending upon the size, if you have got two different kind of guest molecules, depending upon the size of the guest, they will either occupy the x or y. Large size will go to the x side and small ones will go to the y side. Same is for the S2 structure. And what is the cavities per structure is 2. As you saw, there are two cavities of y, and there are 6 for the x, and here it is y is 16 and x is 8, and the average cavity radius is 3.91 in angstroms. This is 4.33, 3.902 and 4.683. This is the cavity radius. So, there are small differences in the cavity radius here for the S1 and the S2 types. What is the most important thing from this data is to see that the unit cell formula is different, and what are the cavities available, the number of these cavities, and depending upon the number of the cavities and the size of the guest molecules, they will be able to crystallize in different structure types S1 and S2 respectively. So, the next important thing is to look at the size of the guest molecule which is going to occupy the voids which are created in the gas hydrates. So, keeping that in mind, people have now looked at this trend more carefully. So, let us draw this to a particular scale. So, we will take a scale now, and we will start with, for example, we will start with different dimensions. For example, we will look at 3 angstrom, we look at 4 angstrom, 5 angstrom, 6 angstrom, 7 angstrom. So, these are the ranges we are going to see here, and what has been observed is when you have got 3 angstrom, between 3 to 4 angstrom, we have got argon, and at 4 angstrom we have got krypton, then nitrogen, oxygen, methane, xenon and hydrogen sulfide. These increase. So, from krypton to nitrogen to oxygen to methane to xenon to H2S, this increases, the size of the molecules are increasing. Then from 5 angstrom we have CO2, ethane, and we have got further we have got C3H6 as well. Then from 6 angstrom onwards we have got propane, butane, I mean to say the isobutane, and 7 angstrom onwards is N-butane. So, we have looked at all these different guest molecules, and we know that methane is very important because they have a role in formation of gas hydrates and the problems we discussed about gas hydrates. And we also have the other hydrocarbons like ethane. CO2 is a very important gas, and it is important to be able to efficiently capture this gas and then use it for different applications, including propane, isobutane and N-butane. All these different kind of guest molecules can be included in the structure of the host lattice. And if you were to actually look at hydrogen, helium and neon, they cannot be trapped in the gas hydrate structures because they diffuse through the hydrogen bonded bars. So, where are the hydrogen bonded bars? So, as I told you, these are the bars, these are the hydrogen bonded bars. So, this is kind of a cage like structure where the water molecules are present and the voids can now contain the guest molecules. And but hydrogen being very small, helium and neon, these can easily diffuse through the hydrogen bonded bars, and they are now free to undergo translational diffusion, and hydrogen molecules can rotate also inside the voids because of the much smaller size. Now, what has been observed is that now what is the structure type which is obtained when you have these host molecules, when you have these guest molecules with the host structure water. So, they tend to crystallize in S2 type, here they crystallize in S1 type, here they crystallize in S1 type, and here they crystallize in S2 type. And we can now find out the hydrate numbers, the ideal hydrate numbers for a given structure type. So, in S2 what happens is that, let us go back to S2. So, in case of S2, the total number of water molecules 136. In case of S1, the total number of molecules is 46. The total number of available voids is 24. The total number of available voids is 8. Okay, this is something we need to keep in mind for the calculation. So, now we can calculate the ideal hydrate numbers. Now, in case of S2 structure, we know that it is a fusion of 512 plus 512 6 4 structure type. This is 512 plus 512 6 2. This is again 512 plus in this case it is only the 512 6 2 voids which are occupied, and here it is only the 512 6 4 voids which are occupied. Now, if you go back and see why 512 6 4, it depends upon the size, and if the size is small, the corresponding void will be occupied. So, now let us look at the ideal hydrate numbers. So, in the case of S2 type, where we have these guest molecules, the total number of voids which are occupied is 24. We saw that number, and the total number of water molecules is 136. So, this comes out to be 5 2 by 3. This is 5 2 by 3. In the second case, we have got 46 water molecules divided by 8, that is 6 plus 2 8. So, this is 5 6 by 8, that is 5 3 by 4. Here this is only occupying the 5 12 6 2 voids. The number of water molecules is 46, but now only the 5 12 6 2 voids are occupied. As you can see, the 5 12 6 2 voids are the larger number. Okay. So, they are occupied, and that is 6 in number. So, this comes out to be 323. So, this comes out to be 46 by 6, that is 7 2 by 3, and here we are going to have 136 water molecules divided by 8, and that is going to be 17. Okay. So, these are the ideal hydrate numbers to start with, that is 5 2/3 water molecules per guest. This is 5 3/4 water molecules per guest, this is 7 2/3 water molecules per guest, and this is 17 water molecules per guest, depending upon the structure type and the type of voids and the corresponding number of voids which are going to be occupied by these guest molecules, in this case N-butane, in this case ethane and isobutane, and so on and so forth. So, different kind of guests depending upon their size will go and occupy the voids, and statistically they will try to occupy those sites where the number of voids are, where more number of guest molecules can go and sit, that is the available void space is larger. As you can see, even in the last two cases, when the size requirement is more, then it goes and occupies preferably the larger size voids. So, these are the ideal hydrate gas numbers, but in reality what can happen, depending upon the pressure and the temperature at which the gas hydrate formation takes place. So, we discussed that this gas hydrate takes place at very low temperature and under high pressure conditions, because you are essentially freezing these gas molecules to occupy the voids, applying pressure and allowing them to crystallize in the voids. So, sometimes what can happen, they get compressed a bit and they are able to adjust into the void volume. So, we can have more content present in these voids than what is expected from these ideal hydrate numbers, and it can also be lower. So, the real crystal structure can give you a composition which need not necessarily correspond to the ideal hydrate numbers. For example, in the case of chlorine water structure, ideally it should have corresponded to 7 2/3 water molecule. This is what was supposed to have been the case, because it crystallized in the S1 structure type, where the 5 12 6 2 voids were being occupied. So, technically it should have been ideally 7 2/3, but in reality the composition is 12 molecules of water. So, you can have more content present in the voids depending upon the adjustment of the water molecules in the void space. So, with this we come to a close about the discussion on gas hydrates, and now in the next lecture we will go into other kind of structures which form a host like framework into which different kind of gas can be included, which will be based on pure organic molecules, where the pure organic molecules have got specific functionality to form large sized supramolecular structures which have voids and cavities to include gas. Thank you.